Hello again, Physics 20s. In today's lesson, I am going to introduce you to an equation that's referred to as a universal wave equation. And then we are going to talk about what happens when a wave strikes a particular type of boundary. And then lastly, we're going to look at what happens when a wave goes from one medium into another one. However, just before jumping into this, I just want to quickly review, just from last time, what a wave actually is. So a wave is an energy carrier. And the way it works is, for a mechanical wave specifically, you have a medium. And a medium is a region that has a constant density to it, if you want to think of it like that. So this could be like water, for example. So we can represent the water as being made up of a bunch of individual particles or molecules. So we have like a couple particles here. Just draw them relatively close together. The way in which you transfer energy through a wave is through individual particle vibrations. So someone could, for example, just maybe take a pebble and just drop it into the water here. What this would do is it would cause this particle to start vibrating back and forth. It would then collide with its neighbor, cause it to vibrate back and forth, collide with its neighbor, make it vibrate back and forth, collide with this one, back and forth, this one, back and forth, kind of like a domino effect. If one domino falls, then the rest of them fall as well. So what ends up happening as a result of these individual particle vibrations and collisions, you can actually take energy from point A and transfer it over to point B. And we refer to that as the direction that the wave energy would propagate from the source. Now, compare that to an ordinary matter, so not talking about an actual not talking about a wave. So let's say we have maybe like an ordinary object, like a volleyball. And I want this volleyball to carry energy from one point to another one. So I want to take it from point A and I want to get it to go over to point B to carry energy there. The big difference for regular matter is that the actual matter itself would have to traverse this distance to transfer energy from A to B, as where with a wave, just the individual particles vibrate to transfer the energy, but those particles themselves don't have to cross this distance. Okay, so it's just a different means in which the energy is going to be transferred. Learning outcomes are to describe how the speed of a wave depends on the characteristics of the medium, to predict quantitatively and verify the effects of changing one or a combination of variables in the universal wave equation, V equals F times lambda. And then 3, explain qualitatively the phenomenon of reflection as exhibited by mechanical waves. So we're going to start off with the universal wave equation. We're going to do a very simple derivation for it. When you see that word universal, it means that it can apply to any type of wave. And going back to the previous lesson, I started off by identifying the two classes of waves. We have mechanical waves and electromagnetic waves. Mechanical waves require a medium for the energy to transfer through, and a medium would have particles in it, as an electromagnetic wave does not. However, this universal wave equation can apply to both, and we'll definitely use it right now. And we're also going to use it later in Physics 30 when we start discussing electromagnetic waves in more detail. Okay, so let's do a derivation of an equation for the universal wave equation, starting with our really simple uniform motion equation. So when we're talking about the speed here, when I say the speed of a wave, it'd be the speed at which the energy is transferring from the source to some kind of location. Okay, because the individual particles themselves are just vibrating back and forth. It's a matter of the energy that's actually moving at a specific speed. If I go through one cycle in the wave, so again, one cycle in the wave, we're looking at like a transverse wave. We had like a particle and it was vibrating back and forth. So one complete cycle would be the time it takes for it to vibrate up to the top, vibrate down to the bottom, and then come back to where it started. So that would represent one cycle T. So for one complete cycle, the time would be the period, and the distance would just be the wavelength. So in the time it takes that one particle just to go through, vibrate through one cycle, the wave energy would actually cross a distance of one wavelength. Therefore, we'd have an equation that looks like V is equal to lambda divided by T. However, we know there's an inverse relationship between the period and the frequency. Therefore, I would have the wave speed is equal to the frequency of the wave multiplied by its wavelength. And that equation is called the universal wave equation. Now, we're interested in what happens when we change different variables in this equation. So let's say that we go into a slower medium. So I'm going to use two examples of, I'll use different temperatures of water as medium. So we'll say that like we have water that is at a cooler temperature. Okay, cooler temperature water. If you looked at the molecules or particles that make up water that's cooler, I would expect them to be moving slower, and I'd also expect them to be a little bit closer together. So the medium itself would be denser. Now, I'm not talking about freezing the water, because once you freeze the water, then things get a little bit weird. Just talking about cooling the water down. So cooler temperature water would be a denser medium. The denser a medium is, the slower the wave energy would propagate through it. If I then took a medium where I had a higher temperature water, so I'll say like warm water, those particles have a bit more energy, kinetic energy, moving around a bit more, expect more space between them. So that means that that medium would be less dense. If material is less dense, like less material to go through, the wave energy can actually propagate faster through the medium. Okay, so here I've said let's go into a slower medium. So a slower medium would be going from warm water into cooler water. Now, what would happen is if you go into a denser medium, then your speed would be lower. If I look at the universal wave equation, there is a direct relationship between the wavelength and the speed, which means that if you go into a denser medium where your wave energy moves slower through it, because of the direct relationship, you're also going to have your wavelength get smaller. On the other hand, if you go into a faster medium, so a faster medium would be one that's less dense. So that'd be going from like cold water into warmer water. A faster medium is less dense. The less dense a medium is, the faster the wave energy can propagate through it. So V would be higher. And because of this direct relationship, if V is higher, then your wavelength would also be higher as well. So your wavelength and speed increase when you go into a faster medium. Now, this relationship is only true if that is a direct relationship if frequency is constant. And it turns out it is. If you go from one medium to another one, like from a fast to a slow medium or a slow to a fast medium, one physical quantity that does not change is the frequency. Okay, so F here is a constant. So for example, if your wave had a frequency of 60 hertz in the cold medium, and then the wave energy passed into a warmer one, it would still have 60 hertz. The only thing capable of changing the frequency of a wave is the source, the thing that actually made the wave in the first place. So to give an example of this, let's say you have like a body of water. This is like a bird's eye view perspective of it. And you drop a pebble into the water. Maybe you see just like lightly drop the pebble into the water. I expect to see some like really light ripples that kind of like surround this. Okay, so this wave energy would be propagating with a certain frequency. Now, if you then took the same pebble, except this time you like chucked it as hard as you could into the water, I might expect to see more little tiny circles. So the frequency in which I'm seeing these ripples come out would actually be more than. So that's the only way you can actually change the frequency of a wave, is depending on, well, what's the thing that's creating the wave in the first place. But after the wave is created and it goes from one medium to another one, your frequency is held constant. And that allows us to look at that direct relationship between the speed and the wavelength. Okay, now we're going to look at what happens when a wave hits a boundary. And when it hits a boundary, it's going to reflect. Well, some of the wave energy gets absorbed when it hits a boundary, but some of it's also going to hit the boundary and bounce back. The example we're going to use is we're going to look at a string, and the string is attached to a boundary. And we're going to look to see what happens to the wave energy in the string when it hits one of these boundaries and gets reflected. So again, reflected just means it's getting bounced back in some capacity. Case one, we're going to look at a fixed boundary. So what does a fixed boundary look like? Well, say there's a piece of string here, and one person is holding on to this end of the string, and it has it fixed in place. And then the other end, another person is also holding this, and it's completely fixed. And then someone else might just take like their finger and just like flick the string. And if they flick the string like up, you're going to get a positive wave pulse. Okay, so this guy's a positive wave pulse. So I have the string, it's fixed because on the one end, but it's approaching this boundary, which is also fixed. Another person here is holding this piece of string, so it cannot move at the end. And someone comes up and just flicks it. I get a positive wave pulse that is then going to get directed away from the source towards this wall. It turns out when it hits this wall, for a moment, the wave just kind of disappears for a quick instant. But then what happens is it reflects, but it reflects as a negative wave pulse. If you have a positive wave pulse compared to a negative one, if you go from like a crest to a trough, I would say these two wave pulses are out of phase. So what happens is when a wave pulse approaches a fixed boundary, the reflected pulse is going to come back upside down or inverted or out of phase relative to your incident wave pulse. So the incident wave pulse will be the one that approaches the boundary, and the reflected one will be the one that bounces back. They're out of phase. Now, there is an explanation as to why this is true. So like, why does it get it reflected upside down? We can use Newton's third law of motion. Okay, as this wave pulse approaches this boundary, when it actually hits the boundary, the wave pulse itself would exert an upward force on the boundary. Now, Newton's third law of motion tells me is that if the wave pulse exerts a force up on the boundary is then going to exert an equal and opposite force in the reverse direction. So because the boundary then exerts an equal and opposite force in the downward direction, it flips the wave pulse around. So then it reflects upside down and then moves away from the boundary. Case two, we have a free boundary. Now, for a free boundary, if you want a way to visualize this, so we still hold one end fixed. So this person's still holding this end of the string here. It can't move. Now think about this. Say like I have like a retort stand. So here's the base of the retort stand, and its vertical line would be the pole. And pretend there's like a little tiny ring that's attached to the string. So what that means is that this ring can like freely move up and down the vertical length of the pole of the retort stand. So there's nothing restricting its vertical motion. So in this case, if we send a positive instant wave pulse towards a free boundary, what actually happens is for a very brief moment, the wave actually gets super big. So if the wave pulse here was maybe like a height of like 1 centimeter, then for a very brief moment here, it actually doubles in size just for an instant. And then what happens is it reflects back, but as a positive wave pulse. So the immediate question would be, why doesn't it get reflected upside down? Well, because it's free to move. You don't really have this opposing force from the boundary needing to exert an equal and opposite force if the actual wave pulse itself is free to move up. Because it's free to move up, it just reflects back in phase in this situation. So your reflected pulse is either upright in comparison to the instant wave pulse, or it is in phase. Lastly, we're going to look at, in a bit more detail, what happens when a wave pulse goes from one medium into another one. I use the example of like warm and cold water, but that's not the most realistic example. Because I mean, like, you can't just like instantaneously go from a region where the water is cold to where the water is warm. Like, that change in temperature would be gradual. Like if you're comparing the temperature at like the top of like a lake compared to the bottom of a lake, it doesn't just instantaneously go from cold to hot. So we'll use a different example. We're going to use an example where we have a spring where one half of the spring is made of a dense material and the other half of the spring is not. I'm going to refer to the density with the spring constant. So K1 is going to represent the spring stiffness on one half of the spring, and K2 would represent the spring stiffness on the other. So when you actually have a wave pulse move from one spring into another, two things are going to happen. One, some of that wave energy is going to get reflected back. And then two, some of it is going to get transmitted into the other end of the spring. I realize right now this is not going to make a whole lot of sense until I actually show you an illustration. So just bear with me for a moment. Okay, so let's look at the two cases. So case one, we're going to go from a slow to a fast medium. So here's my spring. So on the left-hand side of the spring, I've shaded it in a bit bolder, which means that this left-hand side is made up of a spring material that has a higher spring stiffness to it. The right-hand side of the spring has a smaller spring stiffness, therefore K1 is bigger than K2. So I'm going from a more stiff or a stiffer spring to a less stiff spring. So that would be slow, which is a denser medium, to fast, which is a less dense medium. Now, I have this instant wave pulse, and it's going to approach this boundary right here. This is the boundary where it goes directly from the stiff spring to the less stiff part. Okay, two things are going to happen when it hits here. Some of that wave energy is going to get reflected, and some of it is going to get transmitted. So this is just showing the point where it's about to do something, like something's about to happen where it's going to get split into the two parts. Now, in this situation, what occurs is, so this would be the part that gets reflected. And this would be the part that gets transmitted. Some gets reflected, some gets transmitted. Now, I want to point out just one thing right now, and I'll come back in a moment to point out a second thing. So what we know is that if you go into a faster medium, so let's look at our universal wave equation, V is equal to F times the wavelength. And again, your frequency cannot be affected from going from one medium to another one. So if I go into a faster medium, it means my speed will be bigger. And if your speed is bigger, the wavelength should also increase. So if you look here, if this was, I realize the wavelength, if you wanted a proper wavelength, you'd have to like just kind of sketch out like what a full wave would look like. But let's just pretend that just this little distance right here is some kind of representation of part of the wavelength. Okay, so what happens when you go into the faster medium, since your V is bigger and V is proportional to the wavelength, your wavelength gets bigger as well. So your wavelength actually does stretch a little bit more as a result of going into the faster medium. Other thing to note is the reflected wave pulse, it comes back upright. Okay, and I'll talk about why it's upright and not inverted when I go through case two in a moment here. Okay, I'm going to come back to a couple things and another thing regarding the amplitude in a second. Okay, case two, let's do the reverse. Go from a fast to a slow medium. So in this case, on the left-hand side, we have the less stiff spring, and we're going into the stiffer part. So this case, K2 would be bigger than K1. So we approach that boundary. Now the wave's about to split. Some of it's going to get reflected. Some of it is going to get transmitted. Now in this case, so this wave pulse would be the reflected one. And this wave pulse would be the transmitted one. Okay, so what do I notice here? Again, go to the universal wave equation. So V would be equal to F times lambda. V is directly proportional to the wavelength. If I go into a slower medium, then V would go down. If V goes down, the wavelength goes down. And look what's happening to the wavelength here. Okay, initially, again, this is part of a wavelength. The wavelength is a bit stretched out. And when it goes into the slower medium, the wavelength shrinks a little bit because the speed decreases. Now, the other thing to note is that this time around, the reflected wave pulse gets inverted. Any idea why that might be the case? Like in the previous one, it came back in phase. This time around, it actually came back out of phase. When you go into a denser medium, it's kind of like you're hitting a fixed boundary. Okay, think of like transition into a denser medium as hitting a fixed boundary. Well, what do we know about wave pulses that hit fixed boundaries? When they hit fixed boundaries, they reflect out of phase. So this reflected wave pulse is actually upside down. As opposed to in this case, if you go into a medium where it's less dense, that'll be the equivalent of like approaching a free boundary. And if you approach a free boundary, what happens to the reflected wave pulse? Well, it just remains upright. Now, there is one other thing I want to point out, and it's about the amplitude. So the amplitude would just be the distance from equilibrium, where there would be like no wave energy, to like a crest or a trough. Now, it's worth noting that the amplitude is related to how much wave energy you have. So it means a higher amplitude wave would have a bigger amplitude. Again, if you generate this wave pulse by hitting the spring and just like flicking it with your finger, if you flicked it really hard, I might expect the amplitude to be a bit more stretched out. And if I flicked it very softly, like not so much. The thing is, though, when you split it into two waves, this energy has to be conserved. So, for example, if this amplitude here, I'll make up a number. We'll say it's like 2 centimeters. Okay. When it gets reflected and transmitted, both of these pulses cannot have 2 centimeters of amplitude, because that would be telling you you're actually doubling your energy then. Each of these pulses would have to share some of that energy. So maybe this guy would have, what's in the denser medium, so maybe I'd expect it to be a little bit less energy. So maybe this one has like 0.5 centimeters of amplitude. And then perhaps this guy has like 1.5 centimeters of amplitude. But the key thing is, if you take the amplitude of the reflected one and the amplitude of the transmitted one, if energy is perfectly conserved, which it likely isn't because there's frictional effects, but in the best case scenario, those two amplitudes would have to be equal to the total amplitude of your initial wave pulse. Okay, so there's a few things to look for here, which is like when you go from one medium to another one, your energy changes, therefore the amplitude changes, the wavelength is going to change, and also depending on whether you hit like a fixed or a free boundary, it's going to tell you how the reflected wave pulse is going to bounce back. Just one other thing to note here. So we have this wavelength. The reflected wave pulse would actually just bounce back with the same wavelength. And the reason it's the same wavelength is because it's in the same medium. Therefore, it has the same speed. The wavelength's not going to change. Okay, so it's only the wavelength of the one that goes into the new boundary that does change. Okay, let's do a quick example. Pretty easy one. So it says calculate the speed of the wave shown below if one small square equals 10 centimeters and the period of the wave is 2.5 times 10 to the negative 2 seconds. And again, there's a couple different ways you can think about like what the period actually is. So I find the easiest way for me to think about it is the period to be the time it takes for like a particle in the medium to like oscillate down to a trough and then all the way back up to a crest. But that would also be equivalent to the time it takes for the wave energy to propagate in a perpendicular direction if we're talking about a transverse wave. So that's a direction of the velocity that the wave energy is being transferred. So one period would be the time it takes the wave energy to cross over one wavelength. Okay, anyways, we don't need to worry about that, just to perform the calculation. Okay, so let's look at this. We want to use the universal wave equation. So my universal wave equation is V is equal to F times the wavelength. So first things first, let's calculate what the frequency is. So I know frequency and period are inversely related. So I have frequency is equal to 1 over t, and that would be 1 over 2.5 times 10 to the negative 2 seconds. And then I'm going to get a wave frequency that should be 40 hertz. Now, to get the wavelength, you just need to measure it by going crest to crest or trough to trough. I already have a bunch of work drawn on the crest to crest. Let's go from trough to trough here. So from D to H, that'll be a representation of lambda, the wavelength. Okay, so to calculate the wavelength, lambda, let's count how many squares are between D and H. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19, 20. Okay, so I got 20 squares. And it tells me that one small square is 10 centimeters. So I take 20 squares and multiply by 10 centimeters per square. And now give me a wavelength that is 20 times 10 is 200 centimeters. Now I could convert that to meters, but if I leave it in centimeters, it's going to give me a wave speed in centimeters per second. Really depends on what the problem wants you to do. So I'm just going to keep it in centimeters here. Okay, so universal wave equation, V is equal to F times the wavelength. So this would be equal to the frequency, which is 40 hertz, multiplied by the wavelength, which is 200 centimeters. And then V would be, I think that's 8,000. So the two significant digits, it would be 8.0 times 10 to the third meters per second. And again, we're talking about wave speed. It's telling you the speed at which the wave energy is propagating from one point to another one, not the speed at which the particles are moving. The particles themselves are just oscillating back and forth. Okay, so that's it for this lesson. You can complete the assignment called the universal wave equation. And then in the next lesson, we're going to talk about another wave property that is referred to as interference, and start to look at two-dimensional type problems as opposed to just like wave energy moving in a single direction. What if we looked at a couple different dimensions at once? I'll talk to you then.